Great. So I'm going to introduce the panel, and then I will ask each of the speakers to speak, and then hopefully there will be time for discussion. So the topic, since the second task force / panel of the Academy has been artificial intelligence, AI, obviously a hot topic in the news, both in general and related to biomedicine. I've recruited a few speakers trying to get some balance from across the regions and gender and other types of balance that we have, that we aim for. And it's a question that some of you know, actually I think all of us have been talking about in different ways. I had the opportunity to participate in the Ospedale Italiano conference earlier this week on a panel about it. But so the topic is translational artificial intelligence. What will it take to get all the great basic research that's being done into actual clinical use in an evidence-based way? And there's different components of this. There's also concerns about biased data, biased algorithms, full representation of different groups, so diversity, equity, and inclusion. There's also issues of privacy and the kind of balance between wanting to keep our information private versus wanting to contribute to the corpus of medicine so we can learn from what we do. So I have asked each of these individuals to speak for about 5 to 7 minutes, with the hope that we can also have some discussion afterwards. And I will try to moderate this whole thing. We all know that these meetings can be challenging to do virtually, but hopefully we'll get some good ideas out. And I'm also hopeful from this that whatever activities the Academy continues in the AI panel, that perhaps this can inform that. So I'm going to stop my screen sharing. I'm basically giving, each of the panelists has actually sent me their slides, but I will actually give them the opportunity to present, to share and present from their own computer. And if that doesn't work, we can present from here. We're also in the middle going to show the video from Enrico. And then hopefully we'll have some time for presentation. So our speakers who have already introduced themselves, but you all know them: Dr. Sue Bakken of Columbia, John Holmes of University of Pennsylvania, Enrico from Macquarie University in Australia, Jack Lee from Taiwan, and Brad Mallon from Vanderbilt. And they'll probably introduce themselves as well. So if I will just follow the order that's listed here. So if Sue would like to either share her screen or let me know if I need to, okay, see, she's sharing her screen just fine. So I will in your private chat, if you're kind of getting going over time a little bit, I will start bugging you because I do want to leave some time. So go ahead, Sue.
Yeah, thanks. I was asked explicitly to talk more broadly about scientific publication and diversity, equity, and inclusion, since from that particular perspective. And I will use the example of JAMIA, and I'm hoping in our discussion we can hear from some of the other editors that are present, and editors-in-chief or associate editors of other journals, because we have a lot of expertise in the room on this particular topic. When I became the JAMIA editor-in-chief in 2019, one of the things I really wanted to focus on was what I call consequentialist informatics. Like, I thought it was really important that our informatics methods be applied to really important health problems. I gave some examples in my inaugural editorial. I had no idea what was shortly around the corner in COVID-19, and so it was very easy to become become relevant. But one of the points was focus on an important problem and not so much focused on an incremental methodological improvement. And so this ends up being important in how we actually think about what does an informatics journal, and JMIA in particular, publish in the area of AI. And the main area that we do see papers in is clinical prediction models. We get these types of papers every single day of the week. And most often, papers that get rejected are either because they're focusing on something that isn't clinically relevant, or they're not methodologically innovative, which is one of the places where we see an informatics journal fitting in this particular space. We started out with more of a focus. It started out with health equity. That was something I've been committed to for a long time, and our first double issue under my leadership focused on health equity, and we had 23 papers in that special issue. We are continuing to pay attention to topics relevant to health equity. In February, we have an issue coming out that's specifically focused on issues of sex and gender, and where new data science and informatics methods fit in that. We also have an upcoming special issue on global health informatics that's being led by the Avian Global Health Working Group. And we will be soon putting out a call for papers focused on climate change, which is a health equity issue. And I believe it is also a data science and informatics issue. And that's one of the reasons I was among the hundreds of editors who agreed to publish a general editorial on climate change. And I'm very pleased that Enrique Coyera has agreed to be a guest editor-in-chief, because he's had a long commitment to climate change. In terms of diversity, one of the things we've really been focused on is trying to increase the diversity in associate editors, the editorial board, and the student editorial board. One of the things I think we often find is we really need to start with the young, because we don't have a strong cadre of diverse individuals among the most senior people in our field. So one of the ways we tried to do that is, starting with our student editorial board, was to add explicit question in which they're asked to talk about their contributions to DEI. We also have them critique an article that reflects inadequate attention to race and racism, and look to see, do they identify that as an issue in their critique. We're broadly considering diversity, race, ethnicity, geographic, and also scientific. The thing that we instituted in last year was instituting recruitment of what I call young professionals for the JMIA editorial board. And this has helped to increase our diversity. So these are people, some of them still postdocs, some of them clinical informatics fellows, who are a little less far along in their career than typically we would be appointing to the JMIA editorial board, but we're really trying to target this young group and help them on their path to leadership. And for the first time this year, we're actually calling for volunteers for the editorial board, specifically to enhance diversity. We have been paying attention to racism. There was this very influential blog that came out on giving some guidance on a new standard for publishing on racial health inequities, and we have been paying attention to that in our reviews. And this is an example of a paper that I think did an amazing job in truly addressing the racial construct as more of a lived experience than simply a demographic variable to be included. So we're thinking a lot about how to revise our general author guidelines to take advantage of more attention to DEI. And so thinking about things, the rigorous evaluation of racism in papers that address health inequities, making sure that there are relevant subgroup analyses, that things, avoiding collapsing things into other, really taking an equity and bias lens in tables, figures, and their labels. And the AMA guidelines did come out with some new guidelines related to race and ethnicity. And we are awaiting an additional guidelines from COPE, the International Committee on Publication Ethics, to help in this regard. We're planning revisions specifically to AI as well. We did publish in 2020 a paper by one of our associate editors, Tina Hernandez-Boussard, on the minimum information for medical AI reporting, or the MINMAR standard. We had formed a working group to review the existing guidelines. I found out from Megan Shaw, who's one of our editorial board members, about this paper in medRxiv that indicates if you look across the variety of guidelines available, there are 206 criteria from different types of guidelines on really looking at prediction models for clinical use. So we want to continue to pay attention to that. And thank you for allowing me to share my thoughts on this topic, and I'll hand it off to the next speaker and hope that we can have a nice discussion. And so I guess one of the things I'm saying in closing, specific to how do we get things into clinical practice, I'd say from the perspective of JAMIA so far, like if a paper is absolutely ready for prime time clinical practice and is not methodologically innovative, it probably is not the best fit for our journals, but I think there are other informatics journals that may be better suited for that. And those are my thoughts at the moment. So thanks for your time.
Great. Thank you, Sue. And yeah, so I mean, clearly building the evidence base and publishing it in the right places, I agree is critical. So yeah, well, I guess we'll hold off on comments and discussion until we've seen all the presentations. So let me next turn it over to John Holmes.
Okay, thanks, Bill. Hi, everyone. So I just want to let you know a little bit about my background first before I get started, because I come at this both as an epidemiologist and an informatician. So I'm looking very carefully at the data, but also the inferences that we make from those data using machine learning. And so I'm going to focus specifically on the bias and fairness of both of those. So I offer a proposition here. This kind of proposition has been used many times, but this is just one example, and I like this one in particular. Imperfect models are inherently inequitable, but not necessarily systematically unfair or discriminatory. However, we can avoid unfairness by recognizing its sources and remedies. So I offer to you a model of a model or model creation here. So let's start with the state of the world, and we measure some state in that world, and then collect data. And from there, we do some learning, whatever kind of algorithm you want, whether it's statistical, machine learning, whatever. We develop a model and we take action using that model that affects individuals. And we see what actually happens in those individuals by means of feedback, maybe to enhance or improve the model or actually end up discarding it. But then it all comes back to the state of the world. And we're here measuring it, those data again, or measuring the state of the world via these data to, again, get into this model building loop. So let's start with those data. Any source of data can reflect cultural stereotypes, prejudice against a social or other group, and demographic inequities or inequalities. So discovering patterns in these data means replicating these same dynamics in a machine learning model. This is incredibly important because your model is only as good as the data from which that model is created. A really important point here. And when I say good, I mean fair, unbiased, which is actually then generalizable to the population from which you derive those data. So just keep that in mind, that the data actually perpetuates or can perpetuate what's going on at the population, and the model that you derive from machine learning can actually perpetuate the problems in those data. So here's an example. This comes from ImageNet. Actually, ImageNet is probably the major source. In fact, it's definitely the major source for a lot of people working in machine learning, specifically using things like convolutional neural networks for image recognition and the like. There are at least 14 million of these labeled images right now. Again, lots of people are using these, but they're very much biased on geographical provenance of those data. And as you can see, the United States contributes nearly half of those. But take a look at some of the other sources here: Canada, Italy, Great Britain, and then this very large category of other. We don't really know exactly how well these data are representing what's going on in the individual populations, but we do know that there are very serious problems with these data, and also then the machine learning models that are created from them. There's a great article here, and it just came out this past July in Big Data and Society, on the genealogy of machine learning data sets, a critical history of ImageNet. It's a wonderful, wonderful article, and I recommend it. And I believe that Bill is actually going to make the slides available. So I have some sources at the end you might be interested in taking a look at as well. So there's also underrepresentation due to a small sample size, right? So if we start with the main data here, and we're representing the minority class here, or minority classes in either orange or red, and the majority class in green. So the classes could be disease, not disease, dead, alive, et cetera. There are a number of different ways to think about those, but they've just differentiated from each other. And in this case, the minority class is almost 26% of the data. Now you draw a simple random sample and to develop a training set for your machine learner. And you'll notice now we have a markedly decreased minority class. And this could just happen over and over again by applying the same simple random sample regime. However, you could correct this by using stratified or weighted sample lists. Sometimes people do this with cross-validation. But without those methods, the training set can actually bias an existing representation disparity, which then goes on again to create a model which is heavily biased. So let's take a look at another example here from learning. This is a really wonderful example here that looks at using Google Translate. And here we're looking at typing in two phrases: she is a doctor, he is a nurse, and then looking at the Turkish translation of those. Okay, but if you back translate that Turkish translation back into English, it comes out to he is a doctor, she is a nurse. And by the way, this comes out very similarly in Italian. I tried it there too. So this is not, it just related only to Turkish. And so there was a great article that was done by Calibration, reported in Science back in 2017, showing that labor statistics and the male as norm bias almost perfectly predict which pronoun will be returned in Google Translate. Sort of scary, actually. So let's think about this, what's going on here with the action and the feedback. Danielle Ensign wrote in her book, Runaway Feedback Loops and Predictive Policing, that spurious feedback loops occur when data discovered on the basis of predictions are used to update the model. So this loop here actually can come to be a very problematic issue, especially for real-time learning systems, where we think that, oh, we can just go ahead and apply our machine learner and then we'll update based on its experience over time and without any moderation or monitoring, and that could be a real problem as well. So when we think about assessing fairness and bias in data and in algorithms, we think about this list of the starred items that you see here that actually come from the Google machine learning crash course, which are pretty good. Missing feature values is a big problem. We're dealing with this right now and looking at very large data sets that are coming from electronic health records in the International Consortium for the Clinical Characterization of COVID-19 that Zach Kohani is running. along with about 350 health systems and hospitals across 9 different countries. The missing values there are a huge problem. Are there features that are missing that might affect other features? So there we're getting into the effects of missing values on other missing values and other features which may or may not be missing. And so that gets into characterizing the missingness in the data. Are there any unexpected feature values? And what signs of data skew do you see? And do you see disparities between different machine learning models generated on the same data? Which is a big issue for me as a frequent reviewer and an associate editor myself. I see this kind of thing coming up all the time where authors will propose what looks like a very rigorous testing or evaluation scheme for their machine learner. And they're just testing on exactly the same data with a whole host of different machine learners, some of which are related, some are not related to others by means of their characteristics, and without any real discussion about this, about what the meaning of the results are. So it's a big problem. Then finally, I offer to you this, actually it's a preprint, but a pretty well done one, primarily because it gives you this nice compendium of biases, about 25 of them actually in data and machine learning. So it's a really worthwhile preprint to take a look at. And finally, I leave here a bibliography. If you're interested, again, Bill, if you pass out the slides to people, they will see this. And if not, well, then I'll be happy to share it with you too. They're very useful. And I'd like to point to the very last item on the list, which is Jeffrey Balker's book, a wonderful book called Sorting Things Out, Classification and Its Consequences. I'm primarily trained as an information scientist, and which means I was around people who were very much into classification and bibliometrics and the like. And we had to read this book actually, a much earlier edition of this, by the way. And it's a wonderful exposition of the inadequacies and the biases that are implicit in the ICD-9 coding system. So I highly recommend it to all of you for sharing with your students, and it's a great read. Okay, so I will also turn over the.
Thanks, John. Very interesting. And actually, Elaine reminds me that not only will we make the slides available, but EMEA now has a YouTube channel, and the recordings of this part of the meeting will be posted there. So we'll get the links to all of those things out to you as soon as possible. So our next presenter is Enrico, well known to all of us in the Academy, who chose to present this way while he gets his good night's sleep. But we do look forward to seeing him again.
Colleagues, it's a pleasure to be able to speak to you today, and I'm only sorry that I can't do it in real time. Today, the task for me is to talk to you a little bit about research, reproducibility, and replication in informatics. It's an issue that we don't talk about much and don't think about much, but really is central to the whole scientific endeavor. Research replication is essentially scientists checking independently the results of different scientists. And it should be, as you would imagine, foundational to understanding whether or not the research we do is true or not. Other disciplines have embraced replication. Psychology, for example, has essentially done a big purge of poor quality research. In a major and now very famous study, about 39% of 100 critical results were found to be reproducible. In other words, nearly 60% was not reproducible. And as a general rule, across all disciplines of science, about half of what we do can't be reproduced independently by other people. And that is the state of the world for many reasons. Scientists might introduce design flaws in their experiments. They might make statistical errors. They might have too small a sample size. They might engage in what's called outcome switching or selectively report results, that lovely term p-hacking. And on it is. So it's often the case that we just make mistakes quite innocently, and sometimes we go out of the way to find results to report because we need to have papers in journals. When it comes to health informatics, we don't even really talk about this concept, and it's very hard to find evidence of reproduction. So about 3 or 4 years ago, a few of us set out to look at the state of informatics replication and to whether or not we had what's called a replication crisis in our own backyard. And in that study, 2018, essentially we did a review of replication thinking across all disciplines and tried to find examples of it within healthcare. And the conclusion at that point was, look, we don't even really have a conceptual framework within our discipline to talk about it, let alone many examples of replication. But what was missing though was a serious attempt to work out how much replication actually does happen within health informatics. And that's something that I undertook with a colleague and came out in JAMIA middle of this year, actually. And we looked at clinical decision support research as a good exemplar of biomedical informatics research. And we tried to understand how much of that research actually gets replicated and whether or not, when replicated, we find the same results or not. To go very briefly through methods, since time is very short, we focused on the 28 top biomedical informatics journals that we could find and did a systematic search across all of them. We excluded any study that didn't have a real world trial. So if you were trialing an algorithm on historical data, we excluded you from the study. Found about 4,000 papers, of which it looked like something like 10% seemed to match our search criteria for replication. But after we filtered it all and looked at every paper, only 12 papers out of 4,000, 0.3% were true replication studies. And half of those studies did not reproduce the results from before. So our replication rate, at least in decision support research, which is, I think I would argue, a very good representation of the whole discipline, is 3 in 1,000. 3 in 1,000 attempts to replicate our research. That's low. That's low even by the low bar of other disciplines like psychology, which absolutely said it had a problem. So my first message to you, good friends, is that we in health informatics have a problem as scientists. We don't check each other's homework. We don't really go out of our way to work out whether or not major results actually were true or suffered research errors. The next thing I want to talk to you about, though, throws a small spanner in that, which is that there is this notion of fidelity. When I do a replication study, I make a decision as a scientist about how closely or how much fidelity there is between the original study I'm looking at and the study I try to do now. If we go for a high fidelity study, that's what I would call a truth testing study. In other words, I'm trying to make sure that that original study holds. If I, though, intentionally vary aspects of it, then I'm no longer interested in the truth testing. I want to see if that result reappears in my own domain. So I might look at an original study in CPOE and hospitals and say, well, that was very interesting. I now want to see if that replicates in my setting of primary care. So a very different kind of thing, another part of that spectrum, all based on how much fidelity there is between the original and the final study. In highly computational research, where we have the same data sets, the same algorithms, the same platforms, it by definition should be high fidelity and we should be getting the same result, but not so when we enter into the real world, whereas we all know results change based on case mix, workflow, IT infrastructure, and all those organizational human things like training and culture. So a failure to reproduce an original trial result may be due to flaws, but also it can be due to differences in context, a really important thing to understand. Let me very quickly now give you a sense of what I saw in the data set that I did find. So you may recall in 2005, Hahn et al. Had a very famous and controversial paper where they reported mortality increases following the introduction of CPOE into a pediatric hospital. And as you would expect, there was a flurry of attempts to reproduce that result. What I'm going to do now is show you a heat map based on the methodology, which you can find in detail in the JAMIA paper from middle of this year. But essentially, on the left-hand side, I'm scoring against a set of fairly standard categories. Who were the investigators? What was the method? Population, intervention, setting, trial comparator, and the outcome. And then your score, each of those varies between if it's identical all the way through to it being out of class and not being an attempt to replicate. And so what you see is a scattering of results across all 6 of those replication studies. The good news is if you look at method, that you'll see all 6 studies were either identical or had some sort of substitutable elements, and you could have both in their studies. So they were serious attempts to reproduce the science of that enhanced study, which is fantastic. And then you see though that they are scattered around the design of the intervention, the setting, even the reporting of the outcomes. So the question is, what is going on here and why is there this scattering? And here is one explanation. So I've now compressed on the left-hand side all of those scores into a single score between 0 and 1. 1 is highest fidelity, 0 is no fidelity. And I've spread those 6 replication studies across time. And you can see early on, studies tend to focus very much on trying to be very similar to that original study. So they're trying to test the truth of it. And you can see 3 studies all came out and said, look, we can't reproduce that Hahn study. We don't think it's real. Then further studies came in, including another one by Hahn, looking at other settings or other versions of CPOE. And they were more generalization testing. In other words, does this hold elsewhere? So this is not a pattern I've seen before reported. It's very interesting and makes me wonder what we will see once we get larger sets of replication to look at. So just to finish off, this is a critical issue for us all, my friends. We do need to focus on replication, and we also need to remind ourselves about what I would call algorithmic transportability, this problem that we have that is a foundational challenge, that essentially the technologies we build in one context, by definition, when we shift context, don't work as well. And we need to understand why that is, and we need to make sure that they are working as well as they need to be in a new context. And part of the solution, not the whole solution, part of the solution is to embrace replication. We need to test the truth in contexts that are close as possible. And once we're convinced there is truth in a study design, then we must test that context generalization to make sure that things continue to work as we would like elsewhere. So let me finish up. I think we all have a challenge. And the first challenge is that we need to check each other's homework. We need to make sure the science of what we do actually is real. The results we report are robust. And if that is the one message you take away from today, I will be more than pleased. Thank you very much.
Thank you, Enrico, who, of course, unfortunately is not here. And I know that some of you have questions. I think maybe what we'll do is, after the presentations, we'll open up the floor for comments. I also see that some of you have posted comments in the chat as well. But let's keep moving on. Our next speaker, also well known to all of us, is Jack Lee from Taipei Medical University. So go ahead, Jack.
All right, so I guess most of you know about me. I'm also the editor-in-chief for BMJ Health and Care Informatics. And after the next meeting, I'm going to be the president of EMEA. So I'm going to show you some examples. I mean, most of the speakers gave us a very good framework to talk about the translational research, or how to translate AI, and what would be the problem to translate AI projects into clinical settings. And we've seen examples after examples of translating AI projects into a clinical setting and failed. Just like, we do have a statistics that 75% of the HIT project failed. I guess AI would not be better than any other HIT project in the past anyway. But one of the very visible failure was the one from Google on the diabetic retinopathy recognition, image recognition of a fundoscope for the retinopathy from diabetes. They translate the whole project into a Thailand hospital, and it was not working very well. So I'm going to give you one example that's addressing the medical errors. And we know medical errors has been a problem, and it's been a rising problem, and it's become one of the major causes of death. And the reason being, of course, we're facing a uphill battle with the aging population, not to mention COVID-19. Actually, COVID-19 became a major challenge of medication errors for all the patients who have COVID-19, because as far as we know, many of the comorbidities are actually affecting the treatment of COVID-19. And all the comorbidities have their own drugs. And you need to try a lot of drugs. Even prednisolone or dexamethasone on COVID-19 patients, and create other problems of drug interaction and drug errors. So we're facing this uphill battle with the aging population. People are coming to the hospital with polymorbidity, a lot of different diseases, and we give them polypharmacies in response, right? And we have shorter visit time per patient, especially, and these problems are especially bad during the pandemic. And we always have new drugs, new exams, new procedures, and a lot of increasing complexity. So medication error has become something the WHO actually want every country in the world to focus on. And since 2017, they have a project that they want to reduce medication error by 50% in the next 5 years. And they estimated it cost more than $42 billion per year for the countries. So we developed something called ESOP, or AI Enhanced Safety of Prescriptions, that's focusing on prescribing errors. So as you know, in the US, there's probably 4.5 billion prescriptions per year. And if there's only a 7% prescription error, that give you hundreds of millions of errors, right? And in terms of of course, there are many different types of medication errors, and I'm only talking about prescription errors. So you could have diagnosis that you omit. You can have diagnosis that should be there and you did not put there. That's omission, or it should not be there and you put it there. That's a mistake, right? And same for drugs. Especially drugs, because there are so many confusing drug names, like Lassa, look alike and sound alike. Sure. And again, the problem that I have already talked about with short-term patient encounter and polymorbidity with aging population. So we have a super polypharmacy kind of population. So in order to handle the problem, we actually train our machine with a lot of prescriptions, like 1.3 billion prescriptions. And that's actually filled with 2.7 billion ICD codes, 5.2 billion medication codes. And if we do it one by one, there's 80 million drug medication and 2.2 million medication association explored. So eventually we use the machine learning. So this is the math that's behind. If you're interested, that this is the paper that you probably you can take a look at. We published the method we published in 2013. And then after 5 years, we finally get it to run on one of the hospitals. And it takes, of course, a long time to do it, and we need to go through a lot of clinical trial. So yeah, so in 2020, this is kind of one of the validation, the validation process that we published about this system. and then we discovered that there's some imperfection with the algorithm, and we improve it. This is in 2021 we try to that actually triggers some of the problems that was discussed in our previous several speakers. We try to use the system that we trained in Taiwan to handle prescription errors in the US. So we moved to Brigham and Women's Hospital, and with the training, with the machine trained by Taiwan's data, we only get a 70% accuracy. So we use a local. We also use about 600,000 prescriptions from Brigham and Women's Hospital, and we did a hybrid learning, and eventually we were able to reach about 85% accuracy, which is consistent to a Taiwanese data set that's used in Taiwanese hospitals. So that's kind of the problem or the experience that we have from international transferring of a machine learning or AI system. So it's published in JMIR. So if you're interested, you could also take a look. So the ESO model was observed over 80% accuracy. That's overall mostly in Taiwan, but when we moved to the US, it dropped to almost 10%, like 70%. Although you would imagine that, you know, drug and diagnosis, the medical principles are the same across the world, but the habits and the behaviors are not exactly the same. For example, there are more opioids. There are much more opioids prescribed in the US system than in our system. So our machine did not actually sufficiently train for handle all the opioids and the painkillers. So we have to do a hybrid learning in order to accommodate that. So eventually our trigger rate is about 1 to 2%, meaning every 100 patient you get 1 or 2 alerts, and the PPV is about 40 to 60. That means every 2 alerts, 1 will be a real alert. I mean, a real useful alert. So currently we're running in 5 hospitals, and it's already processed more than 2 million prescriptions live. And the physician agree rate is about 50%. So that's quite consistent to our PPV. Although it doesn't mean that physicians agree everything that's correct, or everything they agree were correct, you know, or everything they disagree were incorrect. But I mean, the percentage is about the same. So so far we have averted about 10,000 inappropriate prescriptions, but from a model establishment to clinical trial to real clinical use, it took us about 7 or 8 years, and numerous clinical trials to actually get it done. Okay, that will be my report. Thank you.
Great, thank you very much, Jack. Very, very interesting. So we'll have one more presentation from Brad Mallon from Vanderbilt, and then we'll attempt to have some kind of discussion and dialogue. Are you? You may be on mute. Oh.
No, I'm just trying to make sure that I get up and running.
Okay.
All right. So everybody can see my screen.
Yep.
And you can hear me, so I'm not muted anymore. Okay. So so this is one of those times where you really wish that you had the ability to rewrite your presentation after you've heard what everybody else has had to say. But it's really a great set of presentations that we've seen so far, and I think helps set the stage for what the opportunities and the challenges are that we're running into. So when Bill was putting this together, he asked, could I talk about some of the issues associated with privacy and some of the relationships between privacy and utility. And so I wanted us to think a little bit about some of the potential things that might happen that could throw a wrench in our plans. So when we're thinking about this notion of AI, particularly in clinical practice, we're usually talking about how we're taking an individual's record or a set of records and we're submitting it into some type of a decision support tool that's driven by AI. And we're getting back some knowledge, and this may be a recommendation, or it may be a rank order with respect to what options might be and how to handle the patient. And so this is usually done within the context of an organization. And so if the framework is, just driven by pure AI, where it was like, as it was in the 1960s, where it was just rules driven and the rules were based on the knowledge of some human, then this really wouldn't be so much of a concern. But where the tricky thing lies is that we've moved more towards machine learning. And when we're talking about machine learning, we're talking about taking training data and then submitting it into this AI framework in order to derive something that can be used for the management of the new records that are coming in. And so the way that we've been trying to do this at scale is through either de-identification, or in the United States, or anonymization in the world more generally, to support the development of those frameworks, as well as test whether or not they are replicable and reusable across different domains. And so one of the things that tends to come out of this, and I wasn't really going to talk about this until a couple minutes ago, is what happens about consent. And can you really do this without or should you do this in a context without actually getting the consent of the individuals to whom this training data corresponds? And one of the problems that you run into if you actually throw consent on the table is that you run into the bias problem. And that not all people are willing to consent to have their information reused for the purposes of AI. And this is why a lot of advocates of de-identification or anonymization say that they want to take consent off the table because it creates a level playing field, and all data gets considered when you're building your models. Now, that doesn't mean that the data isn't biased to begin with, but at least it mitigates the bias issue with respect to the data that you already have, which is why we've seen this push towards information reuse in this manner. Now, what I just suggested to you was what happens when you are trying to build a system internally within an organization, but where things are starting to head is that the AI systems are going to be built not necessarily locally, but externally, at which point an organization may need to take information that they have and move it into a different environment, such as if you have a company like Google who develops a cloud-based platform for supporting investigation. It's going to be managed in an environment that you don't necessarily have access to. Now, you could ask to have them transfer the framework over to you, but they don't necessarily have to. And so the problem, this is known as a classical problem of where you're sending the data to the compute, right? And so you're sending data out the door. And the question is, what could possibly go wrong? And I think that some of you have heard me say this before. This is a classical study in the United States where if you're using very basic demographics of the patients that you're trying to provide support for, a lot of them end up being unique, so much so to the point where it's almost laughable in saying that they would have any privacy protection at this point. And this isn't a phenomenon that is just in the United States. If you change the geocode, then you're going to see similar phenomenon in Canada and the UK. Similar studies have been done in Holland and Australia, and the list goes on. And it's not just that there's a risk, it's actually been shown that these types of information have actually been used to commit re-identification studies in the past. And this goes on, dates back at least 20 or 30 years now. This is the poster child for this problem. This is William Weld, who was the governor of the state of Massachusetts, who was re-identified in a famous hack back in the 90s that really led to the identification standards that we have in the US and under our privacy rule for HIPAA. So that's one of the things that can go wrong if we're not careful about what we're doing. But so where things are starting to go is shifting away from sharing data in the clear and starting to think about what can cryptography do for us. And one of the ways in which this happens is that secure multi-party computation gives you the ability for one organization to encrypt their data. In this case, we're encrypting the AI model. You could then have an organization encrypt the actual records that they're interested in learning something about. You would then apply a crypto framework. I'm not going to go through the details of this, but basically you can do encrypted comparisons such that you can get results back without revealing any of the data or the model along the way, and then give the decrypted knowledge back to organization A. And so at this point, organization B hasn't learned anything specific about organization A's data. Organization A doesn't necessarily get to learn anything about the model that organization B put on the table unless they want to reveal it. And so you have bidirectional privacy at this point. There are some challenges with doing this. The crypto functions are not completely scalable. They're limited in their flexibility. You'd really find this very difficult to do natural language processing in this domain. And so more recently, within the last couple of years, what we've seen is a shift towards, or a proposal to move towards what are called secured enclaves. And what that allows you to do is it allows you to create an environment that's tamper resistant within somebody's machine. You can even do this out on the cloud. Microsoft is starting to stand these up, as is Amazon. And what's really kind of cool about this is that Intel has created this capability within what's called their SGX chips, which stands for software guard extensions. But what's fascinating about this is that the criticism until a couple of years ago was that you couldn't really do a lot of computation here because it was limited to 128 megs. And then as of February of this year, Intel came out and introduced a new version of this that upped it to 1 terabyte, and it's just going to keep growing in its size and capability over time. The notability of this, as I was alluding to, is that this is a tamper-resistant environment. It's not, the data is not going to be processed in the encrypted form. It's just an encrypted space. But what that means is that you can put data, you can compute over anything you want. It could be natural language data, it could be fully deep nets, whatever you want to do. And so long as you trust that environment, you can do this computation. A couple other things, and I'll yield the floor. I did want to point out that this notion of what I've talked about is protecting the data and the models as they go in, but the models themselves can be disclosive. And so this was, I'm alluding to this story that came out a couple of weeks ago that did this, that showed a hack with respect to synthetic data generators with respect to models. And so what does this mean? So what you see here on the left, each of these is a set of 4 images. The one on the left is the real image. The images that you see to the right, these are, the one on the left is the fake image. The one on the 3 on the right are the real images that correspond to what really do seem to be like the same individual. And what's notable about this is that these are what are called zero-shot inversions, where it means that you didn't have to have the exact original data in order to probe the system. You just needed to have something that was potentially similar. And so these are what are known as membership inference attacks. And why they matter is that what it says is what's possible is that you can have a user that they can test if the features of someone that they know are in the training data associated with that model. And so this would require knowing certain features about somebody. But it also leads to the secondary problem that says that if you don't know everything about them, then you may be able to predict something new about them that you didn't know beforehand. And so this is really where the rubber meets the road, in that you can prove that somebody's in the training data set, and you can prove that you can learn something new about them as an artifact. So there is a way to address this problem, but a lot of the way in which the machine learned models have been developed over the last couple of years they're not really cognizant or addressing this issue. So finally, I just wanted to point out this whole framework, the secure framework, can actually be extended to account for multiple organizations simultaneously, so that you can do distributed learning. And so that if you don't have enough information at a single organization and you wanted to do, let's say, like a meta-analysis, or you even wanted to do a pooled analysis, you can do it in an encrypted way across a series of organizations. And so if you want to see how we did this in the context of integrating data for COVID-19 investigations, I'd send you the Jean-Louis Ricero's paper, which came out in JAME late last year. So what are we worrying about? The quantity and the diversity of the organizations and the users is going to continue to grow, and that's going to make management a bit of a nightmare as we start to democratize the AI technology. Secondly, the data is going to become more detailed and complex, and why that matters is that if you do risk analysis to try to say, are we doing enough to protect our patients, like when we're sending their data out into these AI frameworks, the simpler models are easier to get a handle on with respect to the risk. As the amount of data grows exponentially over time, this is going to become really challenging. More importantly, and possibly even more challenging, is the fact that every single approach that I just talked about will have its own level of risk. But what exactly is an acceptable level of risk? This requires discussion, and even getting agreement within a single country, let alone across countries, is going to be non-trivial. And then finally, I just want people to recognize that it's likely that we will see breaches happen. There will be intrusions, and that's normal. It's unfortunate, but you're never going to be a perfectly secured system, and we really just need to be prepared for figuring out how do we educate and how do we make sure that we're transparent about what we're doing, so that we can get in front of this and make sure that we're not caught unawares. So I will stop there, and I will yield the floor.
Great. Thank you, Brad. And I want to thank all of the speakers for a kind of mix of different talks, looking at different aspects of this problem. So we have about 10 minutes for comments and discussion. There's a few comments in the chat. People can unmute. If it starts to get a little bit unruly, I may ask people to use the hand raise function. But let me open up the floor for any questions or comments.
Vimla raised her hand.
Yes, thank you. I find the discussion very interesting, and all of them very, very important from different perspectives. I just wanted to add one thing, that one of the biggest challenges that we are going to face in translating scientific research into the clinical practice is that we don't think much about the practice when we develop the AI systems. So keeping in mind that many times we want to augment the performance, the human performance, the performance of the clinicians or the practice. And therefore, developing those systems, keeping in mind what is going to be useful for, is going to be very important for translating it. And the problems will come in because we don't always think about it. That's all I had to say. Thank you. Great discussion.
Yeah, great. Thank you. And of course, we only need to kind of think to how wonderful we thought EHRs were going to be based on the research that was done, in the first decade of the century, and then all sorts of new problems and issues, workflow, burnout, et cetera, emerged.
Well, but also along those lines, not to jump in, but
please.
one of the things that we didn't talk about today is the notion of detection of model drift and calibration of the models. So this is something that has really only started to attract attention over the last couple of years, recognizing that the distribution of the data does change over time, the populations change over time, and that if you have clinicians that habituate to the use of a technology under the expectation that the data's distribution is going to remain constant, this is going to become potentially dangerous. And so there's going to have to be guardrails that are put in place with respect to these types of technologies in order to ensure that you don't have like an army of clinicians banging down the door, telling you to turn the system off.
Yeah, great point.
Yeah, that is a great point, Brad. Vimla, I was immediately thinking about sepsis as an example of what you're talking about.
Right.
So, I've been around enough people who have tried to develop machine learning models to predict both the incidence of sepsis and also to predict the course of sepsis in patients in an ICU. And at the end of the day, it's actually about gut reaction. Machine learning models do not perform any better really than an experienced physician at the bedside. And so, but yet you put a machine learner in that place and it interrupts that gut reaction cognitive flow. So it's not just the physical workflow or the temporal workflow, it's also the cognitive workflow that gets interrupted here.
Absolutely. You're right on target. Yeah. Thank you.
Yeah,
Well,
Jack.
Yeah. So, well, after all that discussion, actually, I think we have to recognize that machine learning is just machine learning from human behaviors. So, so whatever behaviors that they learn from, they just behave like that. If they learn from a biased data set, they're gonna behave, biasedly. So there was one early example. There was a Microsoft chatbot. After it was online, people actually give the chatbot systematically a lot of bigotry, anti, saying Nazis good and anti-Jews and anti-women and anti-everything. And then the chatbot start to behave like that. And they did a lot of things. They give the chatbot a lot of positive messages, but they were never been able to. Microsoft were never able to save the chatbot from being took offline. So I think we should not expect AI to be like omnipotent or super balanced or super. I mean, every flaw we have, they're gonna learn from us and they're gonna behave like us. So they're gonna exhibit everything. If we have bigotry, they're gonna show that in the data. If we're biased, they're gonna show that in the data as well.
Great point.
Yeah,
Great point, Jack.
Yeah.
So
Okay.
Kevin has his hand up. He's waiting patiently. Kevin.
I didn't have it up that long, so I haven't been that patient. No, this is a great conversation. Just kind of a rubber meets the road question here. So there will undoubtedly be another pandemic. We will undoubtedly, as an informatics community, be wanting to get ahead of it by, let's just say, developing some tools that are AI and machine learning based at wherever we first learn about the pandemic and being able to broadly disseminate those internationally. Given what we've talked about today, what's the work we need to be doing to be ready for that?
Great question. Do you have any suggestions?
Well, I'll tell you, one thing that I was sitting here thinking about, there's a lot, of course. I wanted to hear from the great speakers we had. But, George was just celebrating the IAHSI meeting, and I'm sure George is still recovering from it from yesterday. But, there's only a few places we can go that have international observational data that could be updated and close enough to real time that we could learn about model degradation, shift, applicability, et cetera. Do we have an infrastructure in bits and pieces that we should be trying to quickly test to see, kind of thinking the way we think about hackathons or what we've done with NLP challenges? Could we start developing some pandemic challenges that actually demonstrate learning and distributability and, the ability to integrate using FHIR, et cetera?
Can I answer that? So before I brought up 4CE, which is the International Consortium for the Clinical Characterization of COVID-19 using the EHR. And it is an international consortium for sure. We're actually in 8 countries technically, but we do have also a footprint in India. And so we have the framework there. We've got data that we can be using for doing exactly what you're talking about. And this has come up occasionally in our calls. We have a call every Friday morning at 8 with Zach and the whole team, typically about 100 people on that call. And the idea of a hackathon has come up. and it sort of gets passed over because we're looking at individual clinical outcomes, and now our attention is drawn to so-called long COVID or post-acute syndromes associated with COVID, which is also a very important thing. But I would love to bring that back to the group, Kevin, and I will do that tomorrow on our call.
Great.
It's a great idea.
Yeah, George, you.
We don't actually, so don't even do the challenge, just go straight to generating important evidence. Like, we don't need to spend our time showing that we can do it. We should just generate the evidence we need. What hypertension drugs should people be taking? When we're generating evidence, this is AI, so it's predictive models, but it's the same concept that we need to figure out the important problems and actually solve them, and not go to proof, no more proof of concept. We have enough networks in the world now that we can actually just do it. Actually, my presentation 2 days ago to that group that John was talking about when AstraZeneca, when the European Medicines Agency turned off, when the European countries turned off AstraZeneca in March, we used this network, the IAHSI network, to run the study and say, clotting is true, but it's rare. We can turn it back on. So that was 700 million people are affected by an informatics initiative, an international informatics initiative directly affecting. So let's do the real things now, and just don't want to do another challenge. Don't want to do another. Hackathons are good. There's study-a-thons. Do the real thing in the study.
Exactly. That's what I was thinking, George. Yeah, it's not so much a hackathon as a study-a-thon, right?
And George, what I would say is that's not, this problem you solved wasn't a last mile problem, but it's an important problem. So I think that there's parts of this that there's no question we don't need to study. Then there is what Emerge has taught us, right? Which is, so now I drop on your doorstep a definition, and I expect that you're going to be able to run it. And that involves an entirely different part of our informatics community, the applied clinical informaticians who may not be here, or the nursing informaticians who are represented as well. I would argue that we've never really tried a complete real world scenario from, okay, here's a therapy that would be great, to here's a group of patients who received an alert based on that in some window of time. But I think you're right. I agree with you that the more time we spend cycling through another developed consortium and governance and IRB, why? So I'm with you on that.
Great. I see a couple hands up. Vimla.
I just want to emphasize that what Kevin said was very important, and what George said, a specific case in point. The more general issue is that why don't we look at how we are dealing with pandemic today, and what are the needs that we have, technological needs, AI needs, so that you can base it on that, on real world, real data that provides the evidence to what we need to do, instead of starting with the tool looking for a problem. So, just generally, what are the hospitals dealing with today? What are the basic needs, and how do we deal with it? It seems to be a simple enough things to do.
Yeah, great. Louis, you have your hand up?
Yeah, so I think it's great. I really like it, all the presentations, but I think we are missing one very important point. At least I have seen in Spain and in other places that people have put things with AI, like chatbots, that may have worked, but actually creating I know some cases are creating even a panic attack into some of the patients that didn't understand the instructions or how to use it. My point is that we tend to focus so much on data and very little on the human factors that are around the quality of the data, how the system is being used, whether it's usability or any risk for using it without the proper training. I think that's something that we need to put more emphasis, especially because from the patient point of view, there will be a lot of issues with literacy.
Yeah. Great. Well, okay, we're just at about time. Of course, if we were all together in a meeting, we'd adjourn and we'd have side conversations and we'd go out for lunch or whatever, which unfortunately is a limitation of this platform. There's so much more discussion to have on this. I hope we can continue going forward. Perhaps the AI panel of the Academy will evolve and address some of these issues. So I want to thank everyone for participating in this, and I think it's been a great discussion. I've certainly learned some new things myself from the presentations. And again, I encourage everyone to stay involved in the Academy. Next year we'll have another round of elections of fellows and another round of elections for officers and so forth. And then I also want to thank Elaine for organizing this and making the whole thing run smoothly. So thank you, everyone, and have a great day. And we'll look forward to seeing each other again. Take care.
Thank you, Bill.
Take care.
Yeah, bye-bye.
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 Bye, everyone.
Bye.
Bye.
Bye.